Mehdi Vaez comes from the physics department of the University of Tehran. It's going to talk about asymmetric and anisotropic heat transport in nanostructure.
Okay, let me thank the organizer for gathering us together here. And it is my first time in Turkey, and I enjoyed the atmosphere and scientific area. I am from University of Tehran, Mehdi Vaez Allaei, from Department of Physics, as well as partial collaboration with the Institute of IPM in Tehran. I will try to discuss about asymmetry and anisotropy and these effects on the thermal transport. I will briefly try to give a brief motivation and what is going on in low dimensions, and then I will give you some insight about our methodology, and then I will go through some results of our group. It has been precisely described by the two first speakers of today that it is a challenging problem, transferring heat from directly to the electricity. And another important thing is heat management that I would talk about them, what is going on. For the purpose of thermoelectricity, if we take a look at the figure of merit parameter, it is needed to decrease thermal conductivity of the system to get better efficiency in thermoelectric devices. For this purpose, it is important to eliminate all carriers in system, even there might be electrons and phonons and magnons and so on. But this is an important issue, that it is important to decrease and have low thermal conductors in different systems. On the other side, we have this plot for the amount of heat dissipated inside CPU. It is an example that we have in technology, and you see that the amount of energy is going to be increased more and more up to even nuclear reactor. And it means that in the same time, it is needed to have lower thermal conductors, higher thermal conductors to dissipate and manage this amount of energy out of the system. It means that both low and high thermal conductivity is favorable, and depending on the system, we should take care. But for the case of low-dimensional systems, what we have is both of them. For instance, graphene has very high thermal conductivity. As shown, it is about 5,000 watt per meter Kelvin, but it is not possible to get the same magnitude via molecular dynamic simulation. It is needed to consider a very new approach has been described precisely by the previous speakers last day and the day before. And in the same time, we have a low-dimensional system with very low thermal conductivity. The difference is 2 orders of magnitude. It means that we have both of low and high thermal conductivity in this sort of system, and we need to manage and get what we need. When we come into the lower dimension, there are some sort of scattering that has been described by Professor Shiga by suppressing the mean free path of phonons. And also there is something else in between. When we have an interface in a system, for instance, we have two perfectly matched lattice, And just by changing the mass of the lattice on the two sides of the system, it might be possible to get something called capital resistance. And it is common for sort of low dimensional system and even large dimensional systems. But when we come in the nanoscale system size, it becomes more important, since it is different rather than what we have in macroscopic system. It is what we call this mismatched interface, and it is called contact resistance. It is about 3 orders of magnitude higher than the amount of boundary resistance that I mentioned in last slide. It means that when we come into lower dimension, it is important to take into account all things as described by Ali, different kind of scattering and so on. But what we could do about heat management? Heat management is somehow different if we compare with electrical conductivity and electronics. We have all things for managing electron carrier, electrons and other electrical carriers, but the case for the phonons and heat transport is completely different. The first idea of having thermal diode and thermal rectification proposed by Starr at 1935, but it takes time. This idea that was composed of buoyancy effect in fluid, that it is better to have a flow in this direction rather than this direction. When we had hot and cold, it is buoyancy effect, and even it is possible for the solid state cases. But when we come into lower dimension, it is possible to have the idea, but the methodology is somehow different. It was after many years, it was 2002 that Giulio Casati and his colleague showed that it is possible to have thermal rectification in lower dimension by interesting idea. If we have if we have asymmetry in the system, 2 types of potentials on the 2 sides of the system, but if there are different density of a state or vibrational density of a states of in different temperature, it led us to have phonon vibrational density of a state mismatch. As you see, when we have forward direction, there is a matched a shared area for vibrational density of a state, and in reverse direction there is no shared area. It means that we have to a lot of scattering at the boundary to carry heat from one side to the other side. It means that when we have a plus or minus heat current, we will have some sort of rectification similar to what we have in electrical conductivity, that we parameterize this parameter by the TR sign. After a few years, experimentally observed by one group, Majumdar group, I think, that it is possible to get thermal rectification in mass-graded carbon nanotubes. And then plenty of efforts devoted to bring the idea into experiments. This is two approach, decreasing and increasing thermal conductivity. It means that we will try to tune thermal conductivity as well as study thermal conductivity inside different kind of system. I will briefly talk about what we have done. We work with just phonon, and there are other contributions. If somebody, Minghu, I think Professor Minghu told us about contribution of electrons as well. There is capital resistance and sort of thermal rectification that I am going to address. But the methodology is, all kind of methodology are not possible to study this kind of problem. For instance, if we consider the asymmetry in the system, it is not possible to take care of all things. This is on a slide was proposed by Professor Wang that describe what is possible to do with different kind of problem, and what we are doing is working with molecular dynamics that has all kind of nonlinearity inside the system, as well as solving Boltzmann transport equation. This is the methodology that I mentioned. We use LAMS package and non-equilibrium molecular dynamics. For lattice dynamics things, we use LAMS and quantum espresso, and solving Boltzmann transport equation iteratively by Sheng BTE package. Let me skip this slide. It has been discussed with Ali previously, and also it has been discussed by previous speaker about solving Boltzmann transport equation. I can hire the idea and go to, into the results. One of the problems that we have studied was thermal rectification in at the interface of graphene and hydrogenated graphene system. As you see, there is a kind of different capital resistance at interface due to the different density of a state at two sides of the system. You can see at different, the green one is belongs to hydrogenated graphene, and the other, the blue one, correspond to pure graphene. As it is seen that there is a considerable mismatch between vibrational density of a state on the two sides of the system, and when we change the direction of heat transport, this amount of shared area can change, and it led considerable thermal rectification. Here is what we have obtained for a considerable length of the system. It is possible to get about 25% of thermal rectification, but the direction is this way, from hydrogenated to the pristine one. There is better heat transfer rather than the opposite direction. Also, we studied the hydrogenated, the same system of carbon nanotubes. Here is thermal rectification for hydrogenated and pristine carbon nanotube, as it is shown. We have also studied the different percentage of hydrogenation on the two opposite sides of the system, and get thermal rectification at interface. The amount of rectification was higher than even graphene case. And this different capital resistance as interface, depending on the two, the direction is clearly seen. It is the vibrational density of a state of the system when we change the direction from hydrogenated to pristine, and vice versa. There is some sort of difference between density of a state, and it led to thermal rectification in the system. It is not the case just for the interface in a given system. It is a little bit more interesting if we bring the idea of layered media. For the case of layered media, for instance, carbon nanotubes, it is possible to get thermal rectification if we use hot and cold heat baths at inner and outer side of the nanotubes. And if we connect inner carbon nanotubes to one heat bath and the outer to the other opposite heat bath, it is possible to get considerable amount of thermal rectification. You can see we have almost about 55% of thermal rectification for the case of multiple carbon nanotube. One of the important things in the idea of thermal rectification is feasibility for experiment, and as Professor Shakuri described precisely, it is very hard to have different temperature in a very small region. And this example of thermal rectification in multiple carbon nanotube may provide the feasibility of thermal rectification in lower dimensions, since if we consider the temperature profile of the different layers of carbon nanotubes here, we can see that the temperature profile for each carbon nanotube is almost the same, but the amount of change is considerable between the layers. It means that we can have a very long inner carbon nanotube and connect it to a heat bath far from that the other side of the system, and it might be possible to have a system of very long connection of multiple carbon nanotube with considerable amount of thermal rectification. To understand more precisely what is going inside the layered media, we studied also 2D heterostructures, and as it is seen here, we have a combination of monolayer, single layer, monolayer, graphene, and it is possible to consider what is going on when we have this kind of systems, and how much of heat transport through a lower sheet and how much from the upper. We studied this by molecular dynamics simulation, and as it is seen, it is some sort of interesting temperature profile. It is one sort of measurement for temperature profile inside the system, and the second one. If we consider each layer alongside the current direction, we could observe some sort of capillary resistance at interface, but it is not correct, and it is fake capillary resistance, since if we precisely take a look inside the system's temperature profile, it is seen that the top layer has different temperature profile rather than lower layer it means that these two layer at this point has not equilibrated with each other. It means that we have an amount of transport between layer at different position in x direction. We measured the amount of transfer between the layers, And as you see, it is some sort of different transport at the interface, and we have different amount of heat current at different place of the system, and it is not a common capital resistance. I addressed these three items of thermal rectification and layered structure. I will try to talk about how we could tune thermal conductivity, especially by non-destructive methods that could be reversible and in a given system. One of them was studied. One of the system was studied was the curvature effect. We showed that by creating a special amount of curvature, local curvature inside the system, it is possible to get, or at least varies, the amount of thermal conductivity in graphene case by a factor of 30%. It means that it is possible to tune thermal conductivity locally and let the system to come back again. There are another kind of tuning thermal conductivity, non-reversible case, by creating sp3 bonds in, for instance, in bilayer graphene. You know that the thermal conductivity of bilayer graphene and monolayer graphene are almost different, but it is possible to get different thermal conductivity by creating sp3 bonds between the layers, and this is feasible by femtosecond laser pulse or electron beam for creating this sp3 bond, and by an amount of 3% of sp3 bonds in bilayer graphene, it is possible to decrease about 70% thermal conductivity of graphene. To understand what is going inside the system is possible by investigating the vibrational density of a state in the case of pure graphene and pure bilayer graphene and bilayer graphene with hydrogenated one. By creating these sp3 bonds, it is possible to break the in-plane thermal transport and change, and as you see, by creating an sp3 bond, this is pristine, and this is the with sp3 bond, the thermal conductivity decrease due to the amount of scattering induced by scattering of some sort of defects. The other case that we studied was this is the comparison between the bilayer and single layer graphene. The other system that we have studied was silicene. Silicene has some sort of ripple, a very small amount of out-of-plane displacement, and by creating a bilayer silicene, it is possible to change the density of vibrational density of a state of phonons. As you see, there is somehow a gap in density of states of phonon for pure silicene, but by creating these bonds, this disappears, and the amount of thermal conductivity increased by almost a factor of 2. It is possible to see the reason. As you see, for the case of bilayer silicene, the acoustic modes has a stronger, almost higher group velocity, and it led to higher thermal conductivity. Finally, I will briefly discuss about the effect of strain as discussed in previous talk as well. It is possible to change by imposing a strain. It is possible to get different thermal conductivity in bilayer silicene. But for the case of bilayer silicene, that we have this structure, it is not very high change in the amount of thermal conductivity. But for the case, for instance, for the case of systems similar to black phosphorus and so on, that we have very out of plane structures, it is possible to impose a strain at the two sides of the system and change the amount of thermal conductivity just by imposing a strain. I have just 5 minutes, and I can say something about our results on the effect of a strain on the thermal conductivity of silicene. As you see, by increasing the amount of strain, it is possible to increase thermal conductivity, but it is an optimum amount of strain, and then again the thermal conductivity decreases. And also we studied the arsenic case, a two-dimensional case of arsenic. In this case, we have a very highly anisotropic thermal conductivity that is possible to consider in heat management especially, and in the same time we have low thermal conductivity that might be possible to consider in thermoelectric effect as well. This is the cumulative thermal conductivity that we have obtained for the arsenic case, and the contribution of different modes in thermal conductivity has been shown. This is a summary of my talk. I talk about the low dimensions and the importance of asymmetry and capital resistance and thermal rectification, as well as a few systems studied for anisotropy. I would acknowledge my colleagues, Dr. Kosari and Ali, and other group member and colleagues from electrical engineering, physics department, other institutes, and these two are my current students. Finally, I would say something about the thermal conductivity community in Iran. It is not very big, but we have some sort of workshop and so on. It was 2 years ago that we had Julia Casati and the other guys, and Reza as well was in the workshop that we had in Tehran, and I hope that someday we could gather together in an activity in Iran. Thank you very much.
Time for some questions.
Thanks for the nice talk. I was wondering, when you describe the rectification effect, do you ascribe all the rectification to mismatch in the density of states, or are there any other reasons? Yeah.
This one?
Yeah, but in your analysis of your molecular dynamics data, you mentioned...
For the case of, for instance, for the case of hydrogenated graphene, we didn't such a very big mismatch when we reverse the direction of thermal conductivity. For the carbon nanotube case, there was.
So, for example, in this picture, how do you, there's quite a difference, a factor of almost 3 between the delta T's.
Yes.
Do you just ascribe that to the difference in the density of states when you heat up? The overlap changes?
Yes.
Is that the only reason, or is there any other?
The only reason, and there is another thing that actually we have changed the symmetry sp3 here, sp2 here to sp3 here, and it led to almost different out-of-plane modes as well. And these sort of things at the boundary can lead to sort of thermal rectification.
If you go to the next page, the density of states that you show, oh, yeah. This is
for the case of hydrogenated bond. That here is the optical modes that due to the very fast movement of hydrogen.
This is the density of states in the bulk of each material?
Yes.
Okay, maybe we can.
Thank you.
My question is about the contact resistance and the Kapitsa
Yes.
resistance. So, do you know, or how much, to what degree you can switch from Kapitsa to contact resistance? Maybe it may be possible to make a transistor for heat.
By creating a vacancy at the interface.
Yeah, I mean, so when the dot is constant or
Almost the same.
you
Uh-huh.
have Kapitsa resistance.
Exactly.
And in the other unit, you have contact resistance.
Yes.
So what is the, let's say, crossover or from each point we can pass through from Kapitsa to contact resistance?
Uh-huh. It depends. I think it is somehow related to the Alice-Stock when we have a sort of for the case of graphene we have sort of pentagon hexagon rings. Sometimes the vacancy size might be very larger than the amount of lattice size, and we can consider it as contact resistance. But the other side, when we could consider some sort of very rare dissociation of bonds, it could be considered a completely matched interface.
I have just a general comment. Overlap of dust does not meaning that modes are coupled. You should check the direction polarization. Maybe you have some polarized in one direction and other is another direction. Is not any more coupled. Also, you should have something inverse participation ratio to detect which mode are extended. If you have two modes that extended and you have finite dust for all of these, this means that there is a coupling. Otherwise, dust is not sufficient.
Sufficient, yes. Modal description is,
not sufficient.
but it is needed to say something about the contribution of heat that has been carried out by each frequency. You are right. Yes, it is possible to get the group velocity of each mode and consider what is the contribution of different mode, and then decide. Yes, you are right. Yes. 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 A modal description can precisely say what is going inside the, even for the case of, it is what we are doing right now with Ali and Asega. Thank you. Thank you very much for coming. I can't hear. First slide.
You talked about the heat generated in silicon transistor should be cooled down, and then you talked about thermal rectification by graphene and so. I didn't get how this thermal rectification by graphene can be implemented in silicon technology. I mean that do you suggest the graphene as a heat spreader, as no graphene nor nano-ribbon graphene are not good candidates for replacing silicon in transistor technologies?
For instance, there is an amount of sufficient criteria to create thermal rectification. One of them is creating complete anisotropy, and as it is shown here by this experimental group, one of the proposed method is mass grading. Mass grading means you make some sort of gradient in mass distribution inside the system. For instance, it might be possible to consider it with creating vacancy and so on, and might be possible with creating some sort of voids and create phononics and engineering of phonon by for creating this I think Nomura group has done something with, am I right, for thermal rectification. One group in Tokyo University has done by engineering the phonon band gap to let thermal rectification in silicon case.
You mean that this can be used as a heat spreader in
I-
transistors?
Yes.
It can be heat spreader. You mean something like simple picture?
Yes, it is possible as well as transistors as well.
You mean gate replacing silicon?
Yeah, I am not. I have not in mind. But for the case of diodes, it is possible to extend it to thermal transistors. But I am not update on the literature.
Okay, I think we got to move to next speaker. Maybe then we can continue the discussion.